Hello everyone. Part A, explain how to change to polar coordinates in R2 using cartoons and formulas. So part A, polar coordinates is another way to locate a point in R2. So first, I'll just draw a cartoon. Here's the XY plane. I'll say it's the XY plane, which means I've named the coordinates. The right-left dimension is X, and the up-down is Y. And if I have a point, XY, here, then what I can do is draw this line from the origin, 0, 0, to that point, and it has some distance we'll call R. And then the x coordinate, right here, is r cos theta. And the y coordinate, over here, this height, y, of the point xy, is r sine theta. And actually, I kind of like to put it over here because I'm in my head thinking of this opposite edge of this triangle, where theta is this angle. So this is an important picture. And this gives a map from R2 to R2. And it goes from the r theta plane. So this is the r theta plane to the xy plane, the xy plane. And what does it do? Well, it sends r theta, this map F, I'll call it. We always call maps F, I guess, to the point r cos theta and r sine theta. Which, by the way, I mean, we named this output space. We named its coordinates x and y. So another way to say this, and you'll often see, is x equals r cos theta. Y equals r sine theta. And so that is the map. Okay, so for example, it sends the point 1 pi over 2. So this is 1 pi over 2 to the point r equals 1, theta equals pi over 2, right here. And it sends the point, in green, 3 pi over 2. This is the point 3 comma pi over 2 in the r theta plane. This is our input, and we send it, and we get the point that is up here. Yeah, so this is how this map does things. The r is the radius, and the theta is the pi over 2 angle. And so this, is a angle pi over 2. And we have to then go out either 1 or 3, depending on which of these 2 points. Okay? So did I explain polar coordinates using cartoons and formulas? Yes, I did. So this map is how to change coordinates to polar. Okay, now what's part B? Calculate the derivative of this change of coordinates map at the point r comma theta equals 1 comma pi over 2, and also at the point 3 comma pi over 2, which is why I already drew those points. Okay, so B. I'll put B in a different color. At the point r theta equals 1 pi over 2. calculate the derivative. Okay, so first, what's our map? Our map sends r theta to r cos theta, r sine theta. The Jacobian is a 2 by 2 matrix. In this case, it's 2 by 2. Its columns are coming from d by dr and d by d theta, the first and second input variables. And so I'd say the Jacobian matrix is, well, I differentiate with respect to r, so I get cos theta and sine theta. That's the first column. Now the second column, I differentiate with respect to theta, and I get minus r sine theta and r cos theta. And those are my two columns. So now I'd say at the point r theta equals 1 pi over 2, the Jacobian becomes what? Well, I plug in pi over 2 into cos and sine, and I get 0 and 1. I plug in pi over 2, and I plug in r equals 1 to get minus 1 and 0. Okay? At the point r theta equals 3 comma pi over 2, Jacobian is, so now I plug in, luckily the pi over 2 is the same, so the only thing that changes is these r's become 3's. So I just get a minus 3. And notice this 1 stayed a 1. There wasn't an r here, so this didn't change. Okay, great. And now, I think that's the data I need, but it asked me to calculate the derivative, and the derivative is a map. So the derivative at a point is a linear map. So because the inputs is R2 and the outputs are R2, well, because the inputs are R2, we will have two components and we will send them to a linear combination of these basis vectors. This is, is at 1 comma pi over 2. This is the derivative. It's a map. You need to specify this map. And here's another map, a completely different map. Well, not completely different. It's almost the same, except over here we have a negative 3 comma 0 at 3 pi over 2. So we get a different linear map at a different point. Okay, and that is it. This is the work I need to show to calculate the derivative.